How do you do, fellow kids? I know usually professor teaches this class, but you got me today. I'm just a regular University at Buffalo student, so you can tell me any secrets you have, or like how to find solutions to the homework. You know, just let me know. You know. All right, I won't be able to keep up the act for 50 minutes, but that's all I got. So let's get started. Project 3 is out. I'm not going to talk about it today, but for those of you itching to get to it, homework 3 is here, enemy AI. There's a few things I want to say about it. There's a lot of starter code. The other section was saying it was intimidating, just opening the thing. There's a lot of starter code, but you don't have to understand like hardly any of it. Most of it you don't have to understand to be able to do the homework. All of the code you write will be in one single class, or all the code you have to write, I should say. You can add more classes and more things if you want. So it will be a little bit of shock value, but I promise you it's not as intimidating as it appears at first glance. So one thing I like to do in all of my courses is I like the end of the course. I think quite a bit about the difficulty curves of my courses. I like the end of the course to taper off in difficulty a little bit. So I like the first homework, the first assignment, to be a pretty gentle introduction to the course. Pale Blue Dot, you know, it's not objectively easy, but it's definitely easy compared to Project 2. I would assume you all agree with that one. And it's like your intro to Scala, intro to 116, intro to unit testing, things like that. And then I'd say Project 2, Task 3 is the peak difficulty of the course. That should be the hardest task. It's designed to be the hardest task, so I hope that you don't agree with that. Well, what do you think the hardest task is? Task 2? Really? Okay. So Task 2 will be the peak difficulty of the course. But I'm fine with that. As long as it's in Project 2, I've done what I set out to do. So Project 2 is peak difficulty. I'll just say Project 2 is peak difficulty because the application objective is the hardest thing of it, but you don't have to do that, so I don't really count that as part of the difficulty curve. And then Project 3 should be a step down in difficulty from Project 2, if I design it that way. That's the way I designed it. If that's not true, let me know so I can update that for future semesters if I'm missing my difficulty curve, my difficulty marks. But it won't be, Project 3 won't be as easy as Project 1. It won't be easy, but it should be a step down in difficulty from Project 2. So hopefully I hit the mark there. So if you're panicking on Project 2, if Project 2 is kicking your ass, and you're thinking, oh my goodness, Project 3 is going to be even harder than this, I'm here to tell you right now that that's not the intent, that Project 3 should be easier than that. I'm hedging my bets by wording a little bit because some of you will be like, Jesse said Project 3 was easier than Project 2, and this project is absolutely a nightmare. So just in case. But I'd say on average, across every student in the course, you'll find Project 3 easier than Project 2. That one I can say. And I don't think Project 3 is too difficult. I think Task 2 of Project 3 is one of the easiest tasks of the whole course. I mean, it's hard to get easier than Project 1, Task 1, but Task 2 of Project 3 is one of the easiest of the course. And it doesn't even require testing. You don't even have to write unit tests for Task 2. Okay. So Project 3, that's more than I even wanted to talk about it. But we are shifting gears into Learning Objective 3. So Learning Objective 2, we learned about object classes, references, inheritance, polymorphism, state pattern. We learned quite a bit of stuff here, and we're done with that, or at least I'm done with that. Some of you might be wrapping up the homework. Some of you might be taking the round 2 or even round 3 quiz and interview things. That's fine. But I'm done with Learning Objective 2. I'm not talking about it in class anymore unless there are questions. Learning Objective 2 for me is done. I'm moving on to Learning Objective 3 content. For Learning Objective 3, we're learning data structures and algorithms, and we're going to learn about linked lists, trees, and graphs, 3 different data structures and each week of the learning objective is a different data structure. So this is linked list week. And I see this as more of a return to form when we get to learning objective 3. And by that I mean, in learning objective 2, learning inheritance, polymorphism, and the state pattern specifically, it's a whole new way of thinking. It's a kind of a mind-bendingly new way of approaching programming that can be quite difficult, just to be blunt about it. Learning objective 3 kind of returns back to computer science. It'll feel like an extension of 115 and then learning objective 1. It'll kind of feel like a continuation of that, where OOP was just a really different way of thinking. So we're kind of returning to like core computer science stuff. Not that polymorphism and inheritance aren't, but they're just levels and levels and levels of abstraction that can be difficult to wrap your head around. And I don't think learning objective 3 has that same feature. Learning objective 3 is more of just learning more computer science stuff that isn't mind-bendingly complex. That's all I wanted to say about that. I don't know how to answer this question. What does grading in progress mean? Does that mean that grading is still in progress? Yeah. So for your interview and quiz, if you can't click on your score and see feedback, that means it hasn't been graded yet. So when your score turns blue and you can click on it and see feedback, that's when it's been graded and uploaded. So some students have their scores. I believe Tuesday and Wednesday labs have been released, but the Thursday and Friday labs have not. I believe that's where we're at this moment. We do grade them on a rolling basis like that. So don't panic that your friend got their feedback and scores and you haven't yet. It's just the way we're grading on a rolling basis like that. We want to make sure that you have ample time to get your feedback. Here, I'll explain a little bit about how the process works. Is we want to make sure you get your score and feedback before this week's lab to make sure that you can make an informed decision whether you need to go to the review lab or not. So if you failed the quiz, you probably want to go to this review lab this week. But if you pass the quiz, maybe you got something better to do with your time, and I'm not going to tell you otherwise. So to make that decision, we need to get your scores released before, we need to get your quiz and interview graded before your next lab section. But we have labs going from Tuesday morning to Friday night. So if we graded them all at the same time, we can't even start until Friday night, and then we have to get them all done by Tuesday morning. That's a pretty tight time frame. Like the TAs have to be available at that exact time. If some of them have like an exam or a project deadline or something, it's just not going to work out. So we start grading after the Tuesday labs, and they start grading on a rolling basis to make sure that they can meet that deadline for everybody. So don't panic if somebody else has their feedback and you don't. It just means you have a lab later in the week than they do. Yeah, so my wife was like, nobody's going to get your costume. And I was panicking a little bit. I'm like, well, I'm going for it anyway. So I'm glad at least somebody got the reference. He's living life on the edge, posting grades the day of lab. I don't think anybody did that. There are no Monday labs, so there's nobody who got their grades, who have lab today and got grades today. But I'm not aware of that happening this semester in 116, where you got your grades the day of lab. But if that did, let me know. It's something we can yell at the TAs and, I don't know, hope that they work faster. All right, any other questions before I get into linked lists? Okay. Well, I have some information before we get into linked lists. I want to briefly revisit arrays. I talked about arrays earlier in the semester very briefly. I'm going to do it very briefly again. A lot of these topics, arrays, maps, which I'm not even going to talk about at all this week, but I have one bullet point of one slide when we start talking about graphs. What was I saying? Arrays, linked lists, maps, trees, graphs. All these data structures, we're going to have a good pile of data structures, 5 of them by the time we're done with this, this learning objective. I'm not going to go in very much depth on them because you have an entire course next semester, CSE 250, called data structures, where you spend the entire semester talking about data structures. So there's a lot of places where I know where the lines are for 116. I'm going to stop at that line and let 250 pick it up later. Sometimes I blur that line a little bit just to give you a little bit of a foreshadow. And 250, I believe they review a lot very quickly, but they review these 3 weeks in like a day. But so there's a little overlap, but there's boundaries where I'm not going to cross them because that's 250's job. And I don't want to overwhelm you. There's no reason to pack a semester of 250 into 3 weeks of 116. Obviously, I can't do that. So where the lines are is mostly runtime analysis. That's a 250 thing. I'm going to show you, let me back up a second. I'm going to show you how to use these 3 data structures, how to use lists, linked lists, which you've been using linked lists all semester. So we're going to look a little bit more in depth on the structure of a linked list, how to use trees and what they are, what's the structure of a tree, and how to use graphs and what the structure of a graph is. When you get to 250, they're going to go in depth of runtime analysis for one, of which, how long does it take for each operation in each data structure. Sometimes I'll mention them off the cuff, but I won't require you to know that stuff. 250 will for sure. It'll be on your midterm and final exam in 250. It'll be all about runtime analysis, proofs, and things like that. So that's kind of where the lines are. So I'm going to leave a lot on the table for 250 to pick up on. But anyway, array, just very quickly. Again, 250 is going to go way into depth on how arrays work. But this is what an array is. It's a sequential block of memory where all the elements in the array are right next to each other in memory. So actually on your RAM stick, if you have an array of 10 elements, those 10 elements are all right next to each other on the RAM stick. And when you ask your operating system for memory for an array, you have to specify how large the array will be. So you go to your operating system, for example, you want an array of size 10 of integers. You go to your operating system and say, I need enough space to fit 10 integers. If your integers are 32-bit, you're saying, hey, I need 320 bits of data, of memory. And then you get that memory, and you get a reference to the first byte of that memory. And that reference is the only thing you actually store in your variable of type array, is the memory address of the first element of the array. And then if you want to access any element of the array, you take the size of an element, so in my int example, 32 bits, multiply that by the index you want to access, and you would work in bytes. So instead of, I'm always worried I'm going to do my math wrong, but I am going to do it wrong, ain't I? Yeah, 4 bytes. You're going to multiply 4 bytes by whatever index you want to reach. So if I want the value at index 2, I'm going to multiply 2 by the size of the element, the number of bytes for the size of the element, add that to the memory address of my first element, and memory addresses are all in bytes. You access a specific byte of memory, and then that's the memory address that you want to access of the element you want to access. This is what we call random access. I can access any element of the array very quickly by doing one multiplication and one addition to compute exactly where the value that I want to read is located. The downside of arrays is that they're fixed size. I can't resize an array, ever. You can't do it. It just can't be done. There are ways that programming languages give you the illusion that your array is changing size, but a fundamental array in computer science cannot be resized. Once you ask for memory for an array, that's it. That's the memory you get. And the reason that is the memory address right after. So I have this array with 4 elements. If I want to add a 5th element to this array, I have to ask the operating system for specific bytes in memory. I have to ask not just for enough memory to store another value. I have to ask the operating system for these bytes, these exact bytes on memory on my RAM stick, because for my array to work, all the values have to be right next to each other in memory, physically in memory. and that memory might not be available. So much so that operating systems don't allow this feature. They don't allow you to say, give me this specific chunk of memory. The only thing you can do is say, operating system, give me this many bytes of memory. It'll allocate that many bytes somewhere in memory and then return to you a reference to the location where it allocated those bytes. And then it'll make sure no other programs are interfering with your bytes that were allocated to you. For this, we can't do this. We can't just say, give me these bytes. Doesn't work. It's not how computers work. But when we have the reference to the first element, and we want to access the second element, we do a little bit of math and access the memory address for that element that we want to access. Random access. And the way we're accessing these memories, I should have my OX here, this is hex, but the way we're accessing these memory addresses is by their index, because RAM itself, your memory itself, is a giant array. That's why we call it random access memory, RAM, because it's one giant array that can be randomly accessed by index. We have this same feature in RAM itself as we do with an array. So all of our data structures that we talk about, they're actually all built on an array because our memory itself is an array, including stack, heap, all of it is just one giant array of gigabytes. If you have 16 gigs of RAM in your machine, you have a 16 gigabyte array of bytes. And that's what everything runs on. All your processes use that for their memory. So linked list is also a sequential data structure. And when I say sequential, I mean that the order matters. When we have a list or an array, those values are in a specific order. I have the first element, the second element, the third element, as opposed to a key value store. Our maps in Scala, our dictionaries in Python, our objects in JavaScript. Those are key value pairs. There's no sense of the first element in a key value pair. That just doesn't make sense. It's just not the way the data structure works. Lists and arrays, these do have a specific order, and that's what I mean by sequential. There is a sequence to the values. So those sequences are built differently between arrays and linked lists, which we're about to talk about, but they do care about the order. And when we first started testing lists, when we didn't care about the order, we had to add some extra logic to our test by sorting both lists to be able to get rid of this sequential property and say, you know what, I don't care about the order, I just want to know if they contain the same elements. We didn't have to do the same thing with our maps because they're not sequential. So the big difference between arrays and linked lists are spread across memory. They're all over in memory in ways that we can't control and ways that we don't care about. But they're spread all across memory depending on where the operating system allocates our memory, which again, something we don't care about. We just care that we have references to those locations. We don't really care where those locations actually are. And each element, which we're going to start calling nodes, each node in a linked list knows two things. It knows the value at that portion of the list, at that part of the list, and a reference to the next node in the list. And that's it. That's all a linked list node knows. That's all a linked list really is. We're going to spend a week talking about what that means. So to get an element, to access an element in a linked list, we're going to have a reference to the first element of a linked list, which we call the head of the linked list. That's going to know the first value in the linked list and a reference to the next node. And we're going to keep following those references to the next node until we reach the end of the list. We're going to know we reach the end of the list because it's going to have null as its next node. Null, if you haven't heard of null before, I assume most of you have, but I might live in a different world where I've just been in computer science for decades. But if you haven't, null is kind of computer science talk for nothing. It means there should, in our case here, there should be a reference to an object there, but there is no reference to an object. There's just nothing. Call that null. The Scala community frowns upon using null. I am going to use null for my linked list. The Scala community frowns on it, and wants you to set up other ways of avoiding the use of null, but null is in the language. It's kind of like return statements. The Scala community doesn't like return statements, but it's still part of the language. I'm going to take advantage of that and abuse that and use it. The reason I'm going to use it is you will see null extensively in 220. So I want to get you used to seeing that keyword null and seeing this concept of null termination. We're going to say that our lists are null terminated because once we reach a null, that means we know we've reached the end of the list. In 220, you'll be using C, and with C, the community and the language uses null extensively to indicate the end of something. You'll use null termination to indicate the end of a string, the end of arrays, which strings are just arrays of characters, and the end of lists. I don't even know if they use lists, linked lists in 220, but if they do, they'll be null terminated. But your arrays and strings are going to be null terminated. You're going to see it a lot in 220. So I just want to get you used to that idea. Here's some code. This is our linked list node class. It's going to have a value, what value is at that location of the list, and a reference to the next linked list node. And that's it, just those two things. Now there is a little bit extra here, some we kind of briefly talked about so far in this class, but now we're facing it head on, is type parameters. So when you create a Scala data structure, you create a list, an array, a map, either variables of the types or the types themselves, objects of those types. You have to specify the type parameter. You can't just create a Scala list. You say this is a list of ints, this is a list of strings, etc. And you give this type parameter. Well, now we're looking at the other side of that, of how to specify that our class takes a type parameter. So when we create objects of type linked list node, we have to specify this type parameter. And in the class, we're saying this class, in addition to its parameter list, which takes values, it also has a type parameter list that takes types. This A is a variable that I named. It's a convention to have type parameters just be one single uppercase character. I chose A because it's the first letter. It was the first one I thought of because it's the first one. But I chose that. There's nothing special to A. I could even call this the type parameter in all lowercase letters. Like that would be a valid name. Your fellow developers would hate you if you go into the industry naming your type parameters that because it breaks convention. But this is a variable that I named, the type parameter, and then I'm going to use that type wherever I need that type. So if I say this is a linked list node of int, then anywhere I see an A is going to be replaced with int. I'm going to have a value of type int and a reference to a linked list node of type int. If I create a linked list node of string, A would be replaced with string everywhere. Not in the code, but for that object or that variable, A would be replaced with the actual type. So A is a placeholder for whatever type I'm actually going to have. And that allows us to create a data structure that can store any type. A might be a type that we've never even heard of before. The Scala developers, when they created their linked list, their list class, they had no idea that we'd create a list of modifiers. They've never heard of a modifier. They have no idea what that class is at all. But we create a list of modifiers, and that's completely allowed because that list takes a type parameter. And we just said the type parameter, set that equal to modifier. And we can create a list of modifiers. We want the same feature of our linked list, so we're going to take a type parameter. What's the difference between a linked list and a list? Nothing. Scala's list is a linked list, and everything we do with this linked list node class, we're simulating what Scala's list actually does underneath the hood. The reason I'm creating my own linked list is because if I was showing the Scala code itself, it just gets really convoluted, very difficult to read, very, very difficult to understand. I don't even know how it works. It's got a lot of really advanced features going on to get it as optimized as it is and as useful as it is. For example, the linked list node class that we're looking at here, in the Scala list, is actually called : like in the code, it's class : of type A. I believe it uses A as well, and then the parameter list. Like the class name is : You have objects of type : and that's just, I'm not going to present that in a lecture, because that's like the worst class name. I'm sure there's a good reason why they did that. It's not good for teaching purposes. So I'm going to call it linked list node and create my own to be able to show you how a linked list works. But this works the same way as Scala's list. It's the same exact thing. Scala's list is, for what it's worth, an immutable linked list. That's the one big difference between the list I'm going to create and Scala's list, is that I'm going to create a mutable list. And without getting too lost in the weeds on what that means, I have vars here, meaning these can change. Scala's list has vals there. They cannot change. You cannot change a Scala list. So list of 135 is the same as the one you made. I'm actually going to run through this code right now. It's going to be the list 531. So it'll be the other way around because I'm prepending. But yes, you have the right idea. But this is prepending, and I'm going to show you why this is prepending. I haven't explained this part of the code yet. But type parameter, the A will be replaced by whatever type we specify. We're going to store the value at this node and a reference to the next node. And that's kind of it. Oops. That's kind of it. That's the structure of a linked list. You all know linked lists. You kind of do. So we're going to talk, of course, this is linked list week. We have a whole week of explaining all the implications of this. But that's it. That's the structure. When a TA asks you in the interview, what's the structure of a linked list, which they should always ask that question in this interview, it's built on nodes. The nodes know the value at that node and a reference to the next node, and lists are null terminated. There's not too much else to say about the structure of a linked list. So let's see how this actually works in memory. It's one thing to see those bullet points and show you that. But let's see how this actually works and how this is going to have a list, which will end up being the list 531. I keep wanting to say 3 first. And how this actually works in memory. I'm going to skip over quite a bit of the minor steps. We've been doing these memory diagrams for 4 weeks now with classes being created with constructors and all that. So I think I can skip a lot of those steps and kind of breeze through them. So we can focus on the linked list specific parts of this. So I'm going to create a new linked list node. I have the constructor, has the parameters, constructor parameters automatically become state variables. We get a reference to the object that's being created in this, and then we return the reference to the object that's being created into this myList variable. So myList contains the reference 350, and that's a reference to this linked list node, which I have a typo. I missed this. I meant to update it, and then I forgot. This should say linked list node, and then I was shortening it. I meant to shorten it LL node, just because I didn't want to write the whole thing out. But then I ended up writing LL none. That should say LL node, short for linked list node. That tripped somebody up last semester, and I felt bad. And I still didn't fix the typo because I forgot. So we're going to create a new linked list node with the values 3 in myList. And this is the part that reading this code and doing memory diagrams, because you'll get a memory diagram that starts off just like this on your quiz, and damn near guarantee that. This is one part that trips students up, is this myList being used twice on this line. So when we call this constructor, we're going to pass the value of myList. The value of myList is 350, a reference 350. We're going to create a new linked list node, which gets the value 3 and next to 350, a reference to this node. And it'll get its own reference, which I made up to be 250. Importantly, we don't care what the numbers actually are, but importantly, These two nodes can be anywhere in memory. I put one at 350 and one at 200. They're at two potentially completely different locations in memory, and then we use references to link these nodes together. Yeah?
So essentially it goes...
Yep. Yeah, and the right side of the equal sign is always evaluated first. And then that evaluates to a value, and then we do the assignment. So when this is being evaluated, my list is the reference 350, and then we do the assignment, and my list is now a reference to the new linked list node that was just created. So we update my list after that node, that value is created, and after it got the reference 350 from my list. And this is why early in the semester, 115, you've seen this a lot, but this is why we have to reassign our variable. So it's not enough to create this new linked list node, which again, this is the same thing. If I had a Scala list and I did 3 : my list, this is the same thing. This is the same exact thing that we're doing here. So when I create this, I'm creating a linked list node that refers to my node. So my first node has the value 3, and then a reference to the next node, which has the value 1, which is the end of the list. But if I don't reassign my list, and my list is still referring to this value 350, this node, then even though this node exists and refers to this node and created that linked list of size 2, my list variable would still be referring to just this list, which would see the value 1 and a next of null, which is just a list with 1. This is why we have to reassign our variables. This is the mechanics of what's happening in memory, of why you have to reassign that variable. Because you created a new reference to a new node, and you need that reference stored in your variable. If you don't assign that, your list didn't change. Nothing changed over here. Nothing changed with this, but we have a new node that refers to it. In fact, this linked list node doesn't even know that this node refers to it. There's no way of knowing that information. In 250, you'll do doubly linked lists, and there will be ways to do that. We're not going to do doubly linked lists in this class, for what it's worth. If that means anything to anyone, we're only doing singly linked lists in this class. I won't even call them singly linked lists. I'm just going to call them linked lists, because we're only going to do singly linked lists. Since I came this far, I should cap that up. Doubly linked list would have a third parameter, which is the previous node, and each node would know the previous node that refers to it and the next node it refers to. So you can go both ways in those lists. That's doubly linked lists. Then the algorithms are all different. There's different things you can do with that, and there's some things you can't do with lists like that you can do with singly linked lists. All right, then we get to our next constructor call. We're going to create another linked list node with the value 5 and next equal to my list, which is currently 200. Create it, return 480, replace my list with a reference 480. And now at this point, my list and any list variable you've ever had, your Scala lists, your variable only stores a reference to the head of the list, head being the first element of the list. That's all you refer to. You don't have a reference to like an entire list. There's really no concept of an entire list. There's a concept of linked list nodes, and you have a reference to the first node in the linked list. So my list stores the reference 480. So when we go to 480, we find the value 5. 5 is the first element of this linked list. And then to navigate the whole list and get the entire list, we're going to follow its next reference. We'll hop to 200. We find the value 3. So 3 is the next element of this list. We go to next, 350, find the value 1. So 1 is the next element of this linked list. And then we see next is null. We hit our null termination, and we say, okay, that's the end of the list. And we see that we have the list 531, but it's kind of an illusion. We just have a reference to a linked list node, which refers to a linked list node, which refers to a linked list node, which refers to null. And that links together these nodes and forms this concept of a linked list. This is how linked lists work. Okay, any questions on this? Because I'm about to go into algorithms. Yes? Yeah, so the A is what we call a type parameter. That means that this linked list node can store any type. And then in this code, we're specifying that type is int. So in this code, we're replacing this A with an int and this A with an int to say that the value that we store is going to be an int, and the next node that we refer to is going to be a linked list node also with the type parameter of int. So we're going to specify that when we create our linked list nodes and say this is a linked list node of int. We could also say string, and then it would store strings, doubles, modifiers, etc. But that's a way of saying this linked list can store anything, and whoever uses this linked list class can tell us what it's going to store at runtime. Yeah?
Is this Scala also stores its back from
So the question, is this how Scala stores its lists, building from the back forward? Not necessarily. So this is if you use the double colon. And this is the recommended way to build a list, by the way. We'll talk about that in depth Wednesday. But this is the recommended way to build a list. If you use value : list, then this is what's going to happen. That's your prepend operator. But you can append to the end of a Scala list with list : plus and then the value. That'll append to the end and build it the other way around, which is not recommended. Because Scala lists are immutable, appending is a much more expensive operation. But I'll save the details for Wednesday on why that is. The short answer is you have to copy the entire list every time you append. But prepending, I might as well go into it. Prepending, when we prepended this node to the list, we didn't touch anything with this list. So if some other variable refers to this list still, that's fine. We didn't change them. We didn't mess with them at all. We just created a new node that refers to that list. So we didn't change anything. So we didn't break those veils. But if we want to append, we do have to change something. We have to change this next to refer to a different node. That does mess with everybody else, and it would violate those veils. So we'd have to copy the whole list and create a new list with our value added. So what can we do with linked lists? Oh, I'm glad you asked. We're going to do these things. The short answer to that is store values. It's a data structure. We want to store a whole bunch of values of the same type. We're going to throw them in a list. The longer answer, what can we do with these things? That's all I'm going to talk about with the structure. So the structure's done. Now it's, what do we do with this thing? Big deal. We have value and next. How do we work with that? And how do we build the methods, some of the methods that we expect from our list? When we build a list in Scala, we expect to ask it for its size. We expect to be able to get an element at a specific location. If I want the fifth element of a list, I should be able to do that. These are some functionality that we expect from our lists. So let's see how to do those. And when I show you these, I'm going to show them as recursive methods. So we're going to get a flashback, I guess. But the first time we saw recursion was more of a foreshadow of this moment right here. We're going to start using recursion a lot this week and next week. So hopefully we're good with recursion. But if not, don't worry, because today we're going to see quite a few pretty simple examples of recursion. And we're just going to start using recursion. With linked lists, there's an argument that you don't benefit from using recursion, that you'd rather just use a loop. And that's fine. I'm not going to stop you from using loops this time. I have no restrictions like I did for homework 2. You can do whatever you want that gets the job done. I don't care how you approach the problem. Whatever you think is most beneficial. However, when we get to trees next week, recursion will be much easier than using loops. And I'll challenge you when we get to trees. I'll challenge you to do what we do with trees using recursion, to do the same thing with a loop. And so far, nobody's taken me up on that challenge. It's really, really difficult to use loops with trees. Recursion is really going to pay off. So I want to start using recursion this week to make sure that you're comfortable with recursion going into trees where we really need recursion. So first, let's find the size of a linked list. So our base case here is if next is null, I know this is the last element of a linked list or a linked list of size 1. I'm just going to return 1. So if next is null, that node is going to return 1. And if next is not null, my recursive step is going to be to recursively call size on the next element, on the next node of the linked list, get its size, and then increase it by 1. So I'm going to assume that the next element gave me its size. So if I'm sitting in the middle of I'm a node in the middle of a linked list, and I need to know what size I am. What size list do I refer to if I were the head of a linked list? Well, I'm going to ask the next node. I'm going to say, hey, next node, neighbor, how big are you? That neighbor's going to tell me, hey, I'm 15. I'm size 15. Well, if they're size 15 and I refer to them, I must be size 16. I'm going to return that as my answer. So once this gets all the way to the end of the chain, if I get down to a node where next is null, that node's going to say, well, next is null, I'm a linked list of size 1, and it's going to tell its neighbor, hey, I'm linked list of size 1, or not necessarily neighbor, it could be anywhere in memory and bounce all around. But, hey, I'm of size 1, that neighbor's going to get the answer, oh, 1, well, I must be size 2, return 2. The next one, oh, you're 2, well, I must be size 3. And just keep adding 1 all the way up the chain until we get to the first element of the linked list, which will return the total size of the entire linked list. ToString, similar. If I'm the last element, I'm going to call ToString on my value and return that. And if I'm not the last element, I'm going to recursively call ToString on next. I'm going to get everything after me in the linked list as a string, and then I'm going to prepend my values ToString separated by a comma. Now, we don't know what the type of value is when we do this. Value is of type A in our code, and A can be any type. We have no idea what type that will be when we're writing this code. Bless you. But we're still calling ToString on it. We have something of literally any type. It might be a type we've never even thought of before, and we're calling ToString on it. And this is the magic of polymorphism. ToString is defined in the any class, bless you, which absolutely every type in Scala extends, either directly or indirectly. Absolutely every type, no matter what the type parameter is that somebody says, I want a linked list node of whatever type, anything. We know that we can call ToString on it because ToString's in the any class. So this is one of the very few methods that we can call on literally anything, and we're taking advantage of that by calling it on a value of the type of our type parameter, which we have almost no access to its information of anything about it, but we can call ToString. One of the very few things we can do. So we're going to call ToString on it in our method. Access an element by location, and I have a typo in this slide too, I'm sorry about that. Apply should be get value at index. This is my recursive call. So to get a value at a specific location, which we think of as indices because we're used to arrays, but linked lists technically don't have indices. They just have locations. To be able to access a value at a location, we have to call access the next reference, follow the next reference multiple times. If we want the value at location 4, so the 5th element, we have to access next and follow that reference 4 times to get to that element. So this is not like arrays where we could just do a multiplication and an addition and get to any value in the array almost immediately with random access. We can't do that with linked lists. We only have a reference to the head of the linked list. So if we want the 5th element, we have to navigate this list and bounce all around memory following next, dot next, dot next, dot next to be able to access that element. This is a very slow operation. Again, runtime I'll mostly save for 250, but this is one case where I want to mention it, is this is an O of n runtime operation to access a specific element of a linked list. So if I have a linked list of size 1,000,000 and I want the last element, that's a very expensive operation. I have to hop 1,000,000 times across memory and read 1,000,000 different locations in memory to be able to find the last element. Very expensive operation. If you recall way back when I was showing my sorting algorithms and I said, this is O of n squared, but my implementation is actually O of n cubed. This is why I was accessing values at a location in a linked list in a very sloppy way, where I was constantly navigating the whole list over and over and over and over again. Very, very slow. The code, if I is 0, I have no hops to do. I'm just going to return this linked list node. And I'm going to return the node itself, not just the value. We'll see why in the next algorithm. And if I is not 0, I'm going to tell my neighbor to go I minus 1 hops. So if I is 5, for example, I call I of 5 on the head of a linked list. That node is going to go to the next node, tell its next node, hey, you have to go 4 more steps. And then it's going to tell its next, hey, you got to go 3 more steps, 2 more steps, 1 more step. And then we get to the last one, hey, you got to go 0 more steps. And that node says, well, I must be the node that my user is trying to access, return a reference to itself, and then that gets returned back up the recursion. If we want to add an element, this is where we get the flexibility of linked lists that we didn't have with arrays. We can add an element wherever we want in this linked list. We do need a reference to the node before the location that we want to add. So we have this list 4, 3, 1, and we say, oh crap, we forgot 2, and we want to add 2 after 3. We need a reference to the node containing 3. We're going to create a new node containing 2, and we're going to update our next references. Everything's by references in linked list. We're going to update our references to splice that new node into this linked list. So we're going to take whatever this node was referring to, which was this node, and set that to the next of the new node, and then update this next to be referring to the new node that was created. In code, it looks like this. We're going to update next to a new node with the value we want to insert, and that new node is going to have a next of the old next of this dot next. So just like we used my list multiple times in the same line when we were creating this linked list in the memory diagram, doing the same thing here. This dot next, use the old value and then replace that value with a reference to the new node. So we can insert in one line of fairly compact code to be able to restructure this linked list to get that new linked list node in there by reference. Deleting is even easier. We're going to update this next to its next. Just cut that node out of the linked list. That node will still exist. It'll still refer to the node containing 1. But when we're navigating our list, we start with the head, we go to next, we go to next. We just completely cut that node out of the list. And we'll never make it to that node again. It's just sitting there doing nothing. Code is even simpler than insert. This dot next equals this dot next dot next. Completely cuts out this dot next out of the list. To find a value, a little more complex, but not too bad. If this node's value is the value we're looking for, return this node. If next is null, and if we got here, the value at this node already isn't to find, and we're at the end of the list, return null, and that'll be our way of saying, hey, this element isn't in the list if we return null. Else, make the recursive call. And we can do these with recursion or iteration. If you use loops in by iteration I mean loops. If you use loops in your homework, or your project 3 code, I'm fine with that. Like, go for it, knock yourself out. But I do recommend getting the practice before we get to trees. But this is how you do the same thing with a loop. Start at the first node, and then as long as we're not looking at null, check this node and advance node to the next. And if we do find it, we'll have this return in the middle, which again, Scala, the community, doesn't like return statements. So we do have an ugly return statement in here that we don't have with recursion. We could get rid of that, but it's a little bit of a pain to get rid of. But you can do these iteratively, if you'd like. All right, any questions? You still use apply if we don't want to use recursion, right? In project 3, you can't use Scala's list. You have to use this linked list node which won't have apply. You could write an apply method if you want. Yeah.
While nodes equal null.
Yes, and we're constantly updating that to the nodes next. So node is it going through the whole list, and eventually we'll set, we'll be at the last node, and its next will be null, so node will be null, and that's when we want to break out of this loop. And then at that point, we can return null because we made it to the end of the list without finding what we're looking for because we never hit this return. So if we ever make it here, we know the value isn't in the list. Yeah, there are no restrictions for project 3. You can use your conditionals again. All right. Have a great day. I'll see you all Wednesday.